All right, so as mentioned in the last video, the focus of this is solving solving absolute value equations algebraically. And essentially what we're going to do here is how we finished off the last lesson. So in general, if you want to solve an equation that has some sort of absolute value aspect to it, what always works is to write in piecewise form. Now that applies to the part of the equation that has the absolute value. And again, we'll look at examples. Once you have something in piecewise form, you want to solve each piece separately. And you should have two equations. So you solve these two equations separately, and then check the restrictions. Because again, each piece we only look at for certain values of x, and we want to make sure the solution we have matches that value of x. So that's it. As always, the best way of learning this is to try it. And so I have this equation here, and I want to solve this algebraically. The only part that's really kind of tricky is the left-hand side. That's the absolute value part. Now I will say we solved this exact same equation in the previous lesson, but we solved it graphically. But if this equation sounds familiar, there's a good reason for that. So I'm not going to worry about the right-hand side of the equation yet. I want to take the left-hand side, the absolute value of 2x minus 5, and I want to write it in piecewise form. One piece will be 2x minus 5. One piece will be minus 2x plus 5. And again, each time I kind of come back to this idea, I say it faster and faster. So hopefully, again, I'm not saying it too quickly. I look at the top piece when 2x minus 5 is greater than or equal to 0. I look at the bottom piece when 2x minus 5 is less than 0. And so I have my two equations, but my restrictions are a little needlessly complex. But again, for each of these, if I just add 5 to both sides and then divide by 2, I can quickly isolate x in each of those inequalities and have nice simplified restrictions. So my two pieces are 2x minus 5, and I look at that when x is greater than or equal to 5/2, or minus 2x plus 5, which I look at when x is less than 5/2. All right, so that left-hand side of the equation, I can write in either of these pieces. And so now I break up that equation into these two different forms. And so one of the equations I'm going to solve is 2x minus 5 equals 5 minus 3x. And this is connecting back to that first piece. So I'll solve this. Now in itself, this is quite easy to solve. For example, I'd add 3x to both sides. Get 5x minus 5 equals 5. Add 5 to both sides. Get 5x equals 10. And then divide both sides by 5. X equals 2. OK. With that said, the last thing I need to do with this equation is just check my solution, x equals 2, with the restriction. We look at this piece when x is bigger than or equal to 5/2. Now 5/2 is the same as 2.5 or 2.5. So I only look at this piece if x is bigger than 2.5. And so the solution of x equals 2 is actually need to be rejected. It's not one of my solutions. And that's what I just did right there, is this third step. Check the restrictions. Make sure our solution for x matches the piece we're looking at. Because again, when x is 2, I look at this piece. So maybe 2 was a solution for that piece. But again, this is where those restrictions come into play. So far, I don't have any solutions. But now let's look at the other piece. So negative 2x plus 5 equals 5 minus 3x. And again, this here comes from this equation right there. I'm looking at this piece. Again, in itself, this is easy to solve. And so I would add, I'll do this a bit faster. I would add 2x to both sides. So I get I get minus x on this side. And I would subtract 5 from both sides. So I get 0 on this side. And so if 0 equals negative x, that means x equals 0. And again, if I solve that a little too quickly, fair enough. You know, like I said, I added 3x to both sides. Oh, actually I subtracted. What did I do there? You know what, my answer is correct, but actually I think it might be a little easier to follow if I do it slightly differently. Add 2x to, no. Add 3x to both sides. It's not wrong to add 2x to both sides, but it's a little bit nicer if I do it this way. because then I get 5 equals 5. Wow, I'm on a roll here. Probably should just re-record the video, but I'm not going to. Take 4. I'm going to add 2x. Take 5. I'm going to add 3x to both sides. There we go. Whew. I get x plus 5 equals 5. I'm going to subtract 5 from both sides. Well, that took 5 times longer than it should have. But either way, I got a solution of x equals 0. But again, I now need to make sure by looking back at the restriction right here. And I only look at this piece when x is less than 5/2, when x is less than 2.5. And 0 is definitely less than 2.5. And so this is my solution and my only solution. Quite ironic, although this happens a lot, that all my mistakes were made or with just this last few steps of solving this equation. And again, you know, that's what happens when we needlessly rush. And I should probably tell myself to slow down a little bit. All right. With that said, I can apply those ideas to any of these equations. OK, so let's look at this one. Again, I can solve this in different ways. The first thing I would do is subtract 6 from both sides. And then so I get the absolute value of 3x minus 4 equals negative 2. Now at this point, I have a choice. I could write this in piecewise form, and I get 2 different pieces with 2 different restrictions. And then I'd solve each of those equations, make them equal negative 2. And then I'd check each of those solutions with the restrictions. And what I'd find is that I'd get a solution for each piece, but I have to reject both of them. And I know that right now, not only because I've done this question already, but because I can see from this step that there's going to be no solutions. And I mentioned this in a previous lesson. The absolute value of 3x minus 4 will never equal negative 2. Absolute value always makes things positive. So there's no way, I don't care what number I put into that, that I can get a negative 2 out of this. So I know this will never have a solution. So I know there's no solution here. But again, if I did actually break it up into piecewise form and solve each of the pieces and check my restrictions, I still should get no solution. I get 2 different solutions for x, but both of which don't match the restriction. So they both have to be rejected. And so again, I'd have no solution. That's it. I kind of like this approach better than actually doing all that extra work. And just remember again, you can't find the absolute value of something and get a negative number. It's not possible. All right, what about this one? So for this one, this definitely can be possible. The absolute value of this will equal 1 somewhere. So let's take the absolute value part and write that in piecewise form. And again, my 2 pieces, one will be exactly the same. One is which I multiply everything by negative 1. And again, I look at this first piece when x squared minus 2x is greater than or equal to 0. I look at the bottom piece when x squared minus 2x is less than 0. OK, now again, all this should sound familiar because we have done all this before in a previous lesson. But you know, where does, let's simplify these restrictions on x squared minus 2x, where it's greater than or equal to 0 or less than. Let's quickly visualize the graph of x squared minus 2x. If I look at the graph of x squared minus 2x, so if I take out a factor of x, I can see the x-intercepts. I know there's an x-intercept at 0 and at 2. I can tell that it's opening up. And again, this is helpful because if I'm trying to look at this first piece about where is x squared minus 2x greater than 0, I can tell from my graph that it's greater than 0 anytime I'm left of 0. Oh, helps if I put a 0 there. Anytime I'm left of 0 or right of 2. Anytime I'm less than 0 or greater than 2. And so that first piece I can now rewrite as when x is less than or equal to 0 or x is greater than or equal to 2. That's when I look at that top piece. I look at the bottom piece anytime x squared minus 2x is less than 0, which I can now see from the graph is between 0 and 2. Okay, so now with that done, now I can look at my two pieces, right? This piece here and this piece here, and make them both equal 1, because that's the right-hand side of the equation, and then check those solutions with my restrictions. And so let's look at the top piece. Let's look at x squared minus 2x and make that equal to 1. All right, so to solve this, if I bring the 1 over, I have a quadratic equation that equals 0. And if I can factor this, then I'll be done right away. But I can quickly see there are no two numbers that multiply to -1 but add to 2, or -2. You may think -1 and -1, that adds to 2, or -2 I should say, but -1 and -1 multiply to +1. And so fairly quickly that won't do us any good. So I can't factor this. So what can I do? Well, I can complete the square. I can take the first two terms, x squared minus 2x, the -1, leave it over here, create a perfect square right here. This would be a perfect square if I had a +1 right here. Again, I take the middle term, the -2, I divide it by 2 and then square it. -2 divided by 2 is -1, times itself is +1. And I have to balance this out by putting a -1 right here. Everything you see in blue is a perfect square, so I can write it as x minus 1 all squared, and -2 equals 0. And now I can add 2 to both sides. X minus 1 all squared equals 2. Square root both sides. X minus 1 equals plus or minus the square root of 2. And add 1 to both sides. X equals 1 plus or minus root 2. All right, so before I go on though, let's look at those two solutions and see if they fit with my restriction, because all of this came from that first piece. And so if I look right here, sorry, I got distracted there. I only look at this first piece when x is less than 0 or greater than 2. Well, if I look at my two choices, really this is 1 plus root 2 and 1 minus root 2. This is more than 2. I know that because the square root of 2 is more than 1, and 1 plus 1 is 2. I could also go to a calculator. This is less than 0 right here, because again, I know the square root of 2 is more than 1. So 1 minus a number more than 1 will be less than 0. Although again, you can go to a calculator. So both of these work with my restrictions. And so both of these are my solutions so far. So now let's look at the other piece. Minus x squared plus 2x, and make that equal to 1. All right, so solving this. I don't like that negative in front of the x squared, so I'm going to kind of rearrange my terms a bit here and put 0 on one side and bring everything to the right-hand side. X squared minus 2x plus 1. Now this can be factored. This is a perfect square. I get x minus 1 times x minus 1. Which means I can see x equals 1. Again, if we can factor something, it's always easier. And then before I decide if that's a solution, let's look back at the restriction here. I only look at this piece if x is between 0 and 2. 1 is most definitely between 0 and 2. So that is another solution. So nothing here got rejected. This had 3 solutions. All right, so again, these are some tough questions. And again, it keeps coming back to quadratics, fundamental part of this course. And let's look at this last problem. So the last problem is I give you a graph, and I want to know the points of intersection between these two functions. There's 4 points here. What are these coordinates of all these points? Well, I know they all have the same y coordinate. They're all something comma positive 2. But what's the something? So really, I'm trying to find the x values of these intersection points. And I can see there's 4 of them. So how can I do this? Well, if I can think of an equation that represents this, then I can solve that equation. And what I kind of see here is a quadratic function that would have had a vertex 4 below the x-axis. Right? That's what I kind of see here. I'm highlighting in yellow. And then the absolute value of that. When I find the absolute value of that, this part vanishes and it flips up to what you see. So one way of visualizing this is what you see in blue is the graph of x minus 3 squared minus 4. That was the parabola I drew, but the absolute value of it. Because again, if I just continue this down here and then keep going on, there's that parabola of x minus 3l squared minus 4. And that equals this red line, which is a horizontal line at 2, which means equals 2. So there we go. This is the equation I'm trying to solve. If I can solve this equation, I can find those exact coordinates. And I can most definitely solve this by looking at what we've done before. So let me write this in piecewise form. What are my pieces? Again, if I look at the left-hand side, is just the exact same thing, x minus 3 squared minus 4. And I look at that piece when x minus 3 minus 4 is greater than 0. That said, instead of me writing all this down, well, maybe I'll do it for a second, but then I'll erase it. X minus 3 all squared minus 4 is greater than or equal to 0. OK, keep in mind, that just means when my parabola that I sketched out at the beginning is above the x-axis. That outputs the y values are greater than 0. And I can just see that's everywhere here, and that's everywhere here. So I don't need to do any algebraic work. I can see in terms of x, that's when x is less than 1 or more than 5. So I'm going to erase this and write when x is less than 1 or more than 5. All right. And then the other piece is when I make the whole thing negative. So negative x minus 3 squared plus 4. Again, the whole thing was made negative. So if you distribute it, the minus 4 becomes a plus 4. And I look at that when I'm between these 2 points. And that's between 1 and 5. And again, I'm doing this sort of stuff faster and faster because these sort of things have popped up a lot in the last lessons. I'll never say they're easy, but this is not the first time we've seen these sort of things. And so now I have my 2 pieces. There's my top piece. There's my bottom piece. I want to make them both equal 2. So let's look at that top piece, the one I've highlighted in green. X minus 3 all squared minus 4 equals 2. All right, so to solve this, I would add 4 to both sides. X minus 3 all squared equals 6. Square root both sides. X minus 3 equals plus or minus root 6. And then add 3 to both sides. X equals 3 plus or minus root 6. That said, I don't even have to check my restrictions because I know there's going to be 4 solutions here. I can see on the graph there's 4 intersection points. So I don't even have to bother checking. That said, the 2 I just found are these 2 that I'm circling up here. Those are the exact values of those. 3 plus root 6 and 3 minus root 6. All right, similarly, let me do the same thing with the second piece. And make this equal to 2. So again, in this case, I'll subtract 4 from both sides. That said, I could, I shouldn't square root both sides yet because I have a negative in front of the x minus 3 squared, but I can just divide both sides by negative 1 or multiply both sides by negative 1. However we look at it, it's equivalent to this. X minus 3 squared equals positive 2. Now I'll square root both sides. X minus 3 equals plus or minus root 2. And then I'll add 3 to both sides. X equals 3 plus or minus root 2. And those are my other 2 solutions, which again, I don't need to check my restrictions because again, I knew right from the very start of this question I was going to have 4 solutions. And what I just found there are these 2 solutions I'm circling now in red. So those are all the exact x coordinates of that. And notice again, if I just look at all the work here, to answer this question, we have to understand the connection between a system of graphs and solving an equation. That's kind of like the lesson of how we understand the idea of what it means to solve something graphically. We had to then, to solve it algebraically after that, we had to understand how to write in piecewise form, the connection to quadratic functions, and then how to solve these quadratic functions, neither of which could be factored, but we could use the ideas we learned from completing the square to solve them. Tough stuff, but we're all done.